Now, over here in this one, you've got figure 1 shows a variable resistor that has a maximum resistance of 25 ohms. So this is a variable resistor, which means it's a coil of wire, and you've got the slider on top, which is basically your connection. So let's say your circuit is connected to X, and then when you move the slider, you can connect however much of the wire you want. So basically, current will be passing through this coil, right? And if you want your slider to be here, this is the only section of the wire the current will be passing through and then leaving through this section here.
Okay.
Yeah?
Yeah.
So over here, if you keep on changing the position of the slider, more and more wire will be connected. If you move it that way, then less wire will be connected.
So the resistance is lower.
Exactly, that's it. So however much wire you are including, the more resistance you will have had in your circuit. Resistance. So the maximum resistance you can have for this, so let's say if you had moved the position of the slider at this position here, then the maximum resistance you will have included is 25 ohms.
Okay.
Okay, now figure 2 shows the variable resistor being used to investigate the variation of current with voltage for a filament lamp. So the normal operating voltage for the lamp is 12 volts. The 12-volt battery has very negligible internal resistance. So the battery itself does not have any internal resistance, and it's supplying 12 volts, right?
Okay.
Now, the position of P is adjusted so that the reading on the voltmeter at its minimum value of 0.75 volts. So this voltmeter here is reading 0.75 volts. And the whole circuit is supplied with 12 volts. So how much do you think is going to the variable resistor?
11.25 volts.
Very good. So 12 minus the 0.75 that's going to the bulb when it is the minimum, essentially minimum is applied to this one. So maximum is going to the variable resistor. The minimum is going here. So basically what you're saying is the slider is such that, let's say if it's in this position, the electrons will have gone through this way, this way, this way, and gone through the whole coil of wire, right? All the 25 ohms, I'm sorry for the mess. But then it's now going through, the rest of it is going through the ammeter and then going to the bulb, right?
Mhm.
So over here, it's taking up the rest of this variable resistor is taking up 11.25 volts. Okay, so now calculate the resistance of the lamp when the voltmeter reading is 0.75 volts. So what can we do? What do you think?
You could do the ratio.
Very good, exactly. So what can we do? So let's say this one is, we don't know the resistance of the lamp, so I'm going to choose it as R1. And let's say this is R2. The variable resistor is R2. So our ratio is, what's the equation?
V1 times R2 over V2.
Very good. So if we just want to find R1, V1 R2 over V2, that gives us, yeah, 11.2. 5 over 3, okay. What's that in terms of decimal points?
1.67 ohms.
Yeah, 1.67 ohms. Okay.
So
Okay, I
that's
think
the
let's do it together in that that
Yeah,
will help you do
that would help.
better. Yeah, so over here, like we said, each of the top markings are 1 millimeters, right? So that's 1 millimeter, 2, 3, 4, 5. But then we can also see the sixth one, right? We can see the sixth marking as well, isn't it? But can we also see the 0.5 here?
Yeah.
Yes, we can see the 0.5 here. Look. So the 0.5 marking is this marking here, right? So
Yeah.
from the main scale, this is our main scale, right? So from the main scale, we have 6.5 millimeters. Now, to this one, we are going to add the thimble scale. So this is the thimble scale, right? This is the thimble scale. There are different names for it. Okay, for now, I'm just calling it thimble scale. So now we're going to look at which one lines up with the zero markings. What is this marking? So this one is 20.
22.
Exactly. So this one is 21. This one would be 22, right? So that's basically 0.22.
Okay.
Okay. So
Okay,
that's
yeah.
basically 0.22. Now, that's millimeters as well. There is another method you can use. So because you're having to find the I and then apply that I over there again, so it's like a 2-3 steps. The other one you can use is the ratios. Do you remember the ratios formula?
Yes. So
Yeah.
R1 over
Yeah.
R2 equals V1 over V2.
Very good, exactly. So if in this one, you don't need to find the current at all, right? So let's say R1 is the resistance of the wire. So let's say R1 is this one, and this is R2, right? So if we did that, then R1 would simply be V1 over V2 times R2, and this will also give you 0.51.
Okay.
Okay, yeah, so it's like
Yeah.
a shorter one. Sometimes like you might find it difficult to calculate the I. So if I just put in the values, V1 is 397 millivolts would cancel out, and that was 931. And then this one was 1.2. So this would give you 0.51 ohms as well.
I think.
Okay, so think about what is this graph for? There must be a purpose for this graph, right? If they've given you a graph, that means that you need to use the graph in some way. So look at what are
If
your
you
axes. So over here on the y-axis, you've got the resistance. On the x-axis, you've got the length. And your question is resistance per meter.
I think what I would do is find resistance. So if the length is in millimeters, I would find it for like a multiple of I think is 1,000 millimeters.
Yeah,
And then I would times that value of resistance until I got the value of resistance for a meter.
but then you would find it for only one particular value, right? How would you know how much it is for whole, like let's say if you've got 5 meters of the wire, right?
Yeah.
You will have to have come up with a value such that the resistance remains constant for each meter of the wire, right?
I would
So,
say draw a gradient, but I wouldn't know what to do with it because the gradient isn't really the resistance.
but what is the gradient? Look, what is the gradient? If you found the gradient, let's say gradient, I'm going to write gradient as M. So if you found the gradient, which is change in Y over change in X, sorry. So what is Y here? Change in resistance over change in length. So resistance over length, which is the resistance per meter.
Um,
Yeah.
okay,
So all
so
you have
you
to
would
have
have
done is
to,
like consider the scale. So you would have had to
yeah,
think about the scale,
convert it.
but this is the gradient. So if you find the gradient of the graph, you will have found the resistance per length. So first thing you will have to do is draw the best fit line. So if I just let's say do uh, line like so, which kind of passes through most of your points, okay? So take care of whenever you're doing best fit line, look at how many points is above the line and below the line. Okay, so
I have a
approximately,
question about
yeah,
that.
go on.
So when I was doing some questions earlier,
Yeah.
and the thing is, I drew my best line of best fit the same way, but the values that I got for my answers were only slightly off the range that they give in the question. So do
Mm.
you think the examiner would forgive that if they're literally like 0.1 off just because that's how
So
my graph looks?
in the mark schemes, examiners are given up to a range within which there has to be the acceptable value, right? So
Yeah,
if your answer is within that range, so examiners are given a range within which they can give you the mark. If your
yeah.
value is within that range, you will get the mark.